My name is John Hurd, and my project is about improving pandemic response policymaking regarding COVID-19 using an informed prediction model that takes external factors into account. Here is the poster I created for the project. I will be guiding you through the sections of the poster one by one. The first section is the introduction and purpose statement. For this project, I built a model that applied on top of traditional models for the prediction of new daily COVID-19 cases, adds the element of periodicity found in the observed data to the predictive models. To do this, I combined a recurrent neural network containing long short-term memory layers with a feed-forward neural network designed for regression. The regression model incorporates the data predicted by the recursive neural network and other data into its calculations. The reason for this is to enable policymakers to compare models computed using data for proposed social distancing and logistical guidelines. This is done in order to choose the best route to combat the spread of COVID-19. The second section deals with the data used in the project. This data comes from the Our World in Data COVID page and the Apple Mobility Index. Here, the new daily COVID cases for January 13th through January 26th are shown in both tabular and graphical format. Here, an example is shown of data gathered from the Apple Mobility Index. This data is mined by Apple from queries directed at their navigation platform. It is divided into three sections: driving, public transportation or transit, and walking. The higher the number, the more people requested directions or other navigational information from Apple on that day. Here are the URLs of the data sources utilized in this project. The next section is the methodology section. It explains the process by which the data was utilized. The recurrent neural network that represented more traditional models was used to estimate the final 60 days of the data. This is data representative of April 22nd to June 26th, 2020. The output of these predictions from April 22nd to May 31st was combined with data representing the day of the week as an integer and data from the Apple Mobility Index. This data was then used to train the regression model. The regression model was then given data representative of the month of June to predict. Here, the recurrent neural network using long short-term memory layers is shown. The figure on the left is a screenshot of the source code in Python used to construct this model. The figure on the top right is the data fed to the model, and the figure on the bottom right is the output. The input is scaled such that all data is within the range of 0 and 1. The output comes out accordingly. In order to convey the output data appropriately, a reverse scaling process was applied to the data. This is the result. As you can see, the data is no longer simply between 0 and 1, but between 22,000 and 32,000. Here, the regression model is shown. The figure on the left is a screenshot of the source code in Python used to construct this model. The figures on the top right are the testing and training sets used by the model. The figure on the bottom right is the normalized output produced by the evaluation of the testing set by the model. Here, the predictions are shown in non-normalized form. This is the results section. It has been determined that the long short-term memory model and regression model combined produce a graph that better represents swells and dips in the number of new daily COVID-19 cases when compared to traditional time series analysis. There is, however, a minor drawback, as the overall error of the LSTM regression model is slightly higher. It can be seen that the data from the traditional model, shown on the left and indicated by the dark black line and arrow, has less accuracy in the context of predicting peaks and troughs than the data from the new model shown on the right. This is important because these peaks and troughs, though seemingly innocuous on a graph, contribute to major consequences when viewed in context. That context being differences of thousands of new cases of COVID-19 in short time frames. The idea of local directional correctness can be effectively utilized by policymakers to plan more effective pandemic response guidelines. In an effort to be fully transparent in reporting the results of the study, major points regarding error have been summarized here. The figure on the left is a table expressing predicted and observed values for both models, as well as error rates for the models expressed as both absolute distance from the observed data and as percentages. The figure on the top right expresses the average errors. It can be said that there is a discrepancy in error values on the same day between models. However, coupled with the knowledge that the average accuracies of the models are comparable, this can be attributed simply to difference in the predicted curves. As such, the new model can be deemed acceptable in terms of error. To summarize, the combined model should be utilized instead of or in concert with traditional time series analysis, as it has comparable accuracy, data that expresses large changes in COVID-19 cases better, and enables the use of more input metrics. Possible further research could include economic applications of the model, a model designed to address influenza breakouts, and research concerned with improving the overall accuracy of this model. This model could be used in economics to improve economic policy making, predict minor recessions, evaluate stock prices using external inputs such as public opinion and CEO turnover rates, and improve the ability to predict the path of volatile stock prices. The model could also be applied to influenza and encourage the adoption of vaccinations among communities with historically low vaccination rates. A version of this model with improved accuracy would improve every aspect of its function and the function of derived models. Thank you for listening.